Some of you may be familiar with the concepts of barotropic instability and the relations to gradient of relative vorticity versus planetary vorticity and so on. There is a related concept here to see if the cyclone vorticity can actually negate the beta effect. Okay, so that's the environmental beta effect. I think in the previous podcast I said this is in the idealized flow, but actually this is a schematic of the asymmetric tropical cyclone calculated by summing symmetric vortex and the beta gyres. The beta gyres here are a result of symmetric tropical cyclone in a more typical environment with non-zero relative vorticity gradient. So it's still a symmetric cyclone, but it's put in a more typical environment, so it's not just the idealized uniform flow we had considered, right? Where are we going with that? So basically you can think of beta of the environment as gradient of zeta environment plus f. So the background weather system or winds that we are in is not uniform non-time varying. It can still be non-time varying, but it has gradients, vertical gradients du dy, which is giving us a background vorticity in addition to the planetary vorticity. So to see if the cyclone beta gyre effects together can cancel the environmental beta, we can see whether the relative vorticity which is du dy itself can have a gradient that is larger than beta. So what is the gradient of meridional gradient of relative vorticity? That's partial squared u partial y squared, d squared u dy squared. So du dy is the relative vorticity. Its gradient in the meridional direction is d dy, which has to be greater than beta in most barotropic instability calculations, as you may remember. I don't want to confuse you, but just in case you're familiar, you see the parallels. So to see what gradient of relative vorticity we will need to cancel beta effect of the environment, we can do simple calculation. I'm just copying the text again from the book. So we need to calculate beta, which is df dy, which is 2 omega over a cosine phi. So you put in a typical tropical cyclone latitude here. Rest of them are fairly straightforward. So you end up with beta of 2.2 times 10 to the minus 11 per second per meter. That's the unit. In general, beta is small in the tropics, but as you get away from the tropics, beta begins to increase. So we have to be aware of that. Sorry, I chopped off the square here. So deduce the value of d squared u dy squared needed to negate the beta effect. So to negate beta, d squared u dy squared must also be 2.2 of the order of 2.2 times 10 to the minus 11 per second per meter. So then we can take typical environmental winds and see what is the gradient required over the weather systems that we are talking about, let's say order 10 to the 6 meters, right? 1,000 kilometers. To solve the simplest form of simplest functional form for d squared u dy squared, assuming beta is constant in our beta plane. Typically, let's say we're on a plane where beta is constant. Make one assumption that d squared u dy squared is d squared u dy squared, so that u is only a function of y. That is, the zonal wind only varies in the north-south direction. So we are again ignoring the u dx term for this simple illustration. Now solving for the functional form of u is straightforward. So du dy is integral of d squared u dy squared. So the vorticity required can be calculated that way. And d squared u dy squared is what we are trying to match beta. So that's integral beta dy. Beta is constant on our beta plane, so it is beta y plus c1, a integration constant, and this is per second because we integrated in y, right? Where c1 is an integral constant, and we recall that we have also assumed beta to be constant. Integrating one more time gives us u as a function of y should be integral of du dy. So put that in there, and that gives us beta y squared plus c1y, c1 is a constant, plus another constant of integration c2, where c2 is another integration constant. For simplicity, let's assume both c1 and c2 are 0, no loss of generalization. That leaves us uy equals 2.2 times 10 to the minus 11 y squared meter per second, right? This is current, so it's meter per second. So that's a tiny number. Now you have to translate this to d squared dy and beta into a change in the zonal winds needed to negate environmental beta between 2 points. So a change in the zonal winds between 2 points is given by du dy. So 2.2 times 10 to the minus 11 y. So in this simple world, moving north or south by just 1 meter will change the winds by 2.2 times 10 to the minus 11 meter per second. What does that translate to our synoptic scales? The synoptic system has spatial scale of order 1,000 kilometers, yes, or 10 to the 6 meter, which tells us that we can negate the beta effect of beta with a change in the u component on the synoptic scale of 2.2 times 10 to the minus 5 meter per second. Obviously too small, right? This is few millimeters, fractions of millimeters per second, which doesn't make any sense considering we are talking about cyclones. So what are we missing? That's what we will see when we come back. Okay, just go through the calculations, very simple, to see where we are headed with that. So we are talking about the cyclone, which can be symmetric, but intrinsically, because of its rotation in a beta environment, it's generating these beta gyres, which were together with the environmental flow is giving us these asymmetries. And now we are trying to see what kind of relative vorticity can actually negate the beta, and the numbers we came up with seem very unrealistic. So we're going to try to explain why we ended up with that in the next podcast. Okay.